Hello everyone, and welcome to the final video on functions. So in this video all we're going to do is wrap up some loose ends. I want to do two more things. The first thing I want to do is I want to just look at a complete example of a program that's been totally streamlined using functions. So I'm going to show you some code that's not streamlined at all, and then I'll show you the same code but where everything has been sort of outsourced to functions, and we'll look at the difference between the two. And this example that I will show you will involve several functions that use passing by reference, just so we can see more of that. And then finally we'll talk about our last topic, which is recursion. So that's sort of the last big function topic. Okay, so before we get to recursion, let me look at this example. So this example is, this code here is Evan Johnson's. This is number one from a while ago. I don't remember. So let's just run this and see what it does. This is that game where you tell it how many empty boxes you want, and then on your turn you place a rock in a box. So I'm going to place a rock in the first box. And now another player can place a rock in some other box, right? And you keep playing until somebody puts a rock next to another one. So right now these rocks aren't next to each other, right? But now if I place a rock at position 5, which is right here, then I lose. Okay, so the first person who places a stone next to another one, that player loses. So again, this is a game you guys all wrote, and most of you wrote this program in different ways. So we're going to trace through Evan's code here briefly just to see what he did so that you can see how I took his code and streamlined it with functions. But before we do that, let me just say that one of the reasons why it's fun to teach a course like this is because I really get to see the cleverness of my students and the creativity of my students in ways that I don't get to see such things in, say, a Calculus 1 course. Okay, there is room for creativity and cleverness in a Calculus 1 course, but there's far more room for such things when you're teaching a programming course. So it really is fun to see how different students solve the same problem, and it's fun to trace through the different avenues students take. So Evan's solution here is clever, but I saw several other clever solutions as well. Okay, so that being said, let's trace through what he did. He gets the number of boxes. Evan wanted the number of boxes to be 3 or bigger. So you don't want a negative number of boxes, for example. Then he initializes the game board. And under the hood, Evan is using zeros and ones to keep track of where the rocks are. So a 0 means there's no rock there, and a 1 means there is a rock there. But what he prints to the user is E's for empty and O's for occupied or something. So anyway, the vector he creates is an integer vector because he's storing things in terms of zeros and ones, but what he shows the user aren't zeros and ones, he shows the user E's and O's. Okay, so he has a check variable here that as long as nobody has lost yet, this check has value 0. And so he asks, where do you want to put the rock? And then he makes sure that they've chosen a legitimate spot to put the rock, right? So the rock has to be inside the game board. That's what these first two conditions say. You don't want place to be negative, and you don't want place to be too big. And also, you need to place the rock in an empty slot. So if the slot isn't empty, so if any of these three things happen, Evan prompts the user to try again. Once he has that valid choice, he changes the 0 to a 1 to denote that now the space is filled with a rock, and then he prints the current game board, and then at the same time he does something else. He checks whether or not somebody has lost yet. So notice how he does that. What would it mean to lose? What it means to lose is that now you've changed a 0 to a 1, and there's a 1 next to you. So what he checks here is, so if boxes at position I and boxes at position I plus 1, if both of those are 1, then their sum is 2. So Evan is checking to see if you've put a rock next to another one by simply seeing if he ever sees a sum of 2 as he traverses through the vector. And same thing for a place -1, right? So I suppose here he's checking both sides, right? But in any case, that's the logic of what he's doing. He's just checking for adjacency, and the way he's checking for that is by seeing if he sees 2 1s in a row. And if you see 2 1s in a row, you get a sum of 2. Okay, so the logic of all this, right, is that he gets a number of boxes, he initializes the game board, he also has a validation check here to make sure the user gives a valid number of boxes. Down here, he gets a position inside the box list from the user, and then he has another validation check. And then here, he tells the user what the game board is, and he checks to see if somebody has lost or not. Okay. So this program is good. It does what it's supposed to do. It does it fairly efficiently, etc. There's no reason that Evan needs to improve on this. But I'm going to show you a way you can streamline this using functions. And of course, when Evan wrote this program, we didn't have functions yet, so there are no functions here. So, whoops. Okay, oh, here it is. Okay, there we go. Okay, so I rewrote his program using functions to do most of the tasks. So let's go back up to the top. I still have an n and I still have a place choice. So n is going to keep track of the number of boxes. N is going to keep track of where the user wants to place a rock. So I start by getting the number of boxes from the user, and then I have this function that's just called make sure number of boxes is valid, and I tell the function what the user chose. So let's go to that function. Make sure number of boxes is valid. So notice I passed the choice the user made by reference, not by value. So that variable itself is passed. And then here's Evan's code. Hey, as long as that n value is less than 3, come on bro, need more boxes, right? And so you get that choice from the user. Because I passed this by value, because I passed it by reference, once the user breaks out of this for loop, that choice they've made, so if n is 6 or whatever, that is remembered up here. Okay, when you pass by reference, the choices you make, the manipulations you make inside your function, those are remembered up top in main. So let's just say that up here the user enters the number 1. Okay, so now n is 1 right here. That 1 gets passed down here, and it's passed by reference. So not just the 1, but the variable n itself is passed. So the 1 and the variable that's storing 1 are both passed. So now down here, you just have this while loop that says, hey, as long as the user is telling you something invalid, you make them choose again. So n right now is 1. So you enter this while loop, and maybe the user, the next thing they do is they enter a -2. Well, that's still not valid, so you do this loop again, and you do it until the user enters something like 7. Okay? As soon as the user enters 7, now n is 7, and you break out of this loop. But not only do you break out of this loop, n now, the variable n, now has value 7. That's true down here, and since you passed by reference, that's true up here as well. Okay? So, if I remove this ampersand here and I pass by value, what I just said would not be the case. So you can update the value of n down here inside this function, but since you passed by value and not by reference, this update down here is forgotten when you go back to main. So when you come back up here to main after the function's done running, n is still going to be 1 or whatever. So I passed it by reference because I wanted this update to be remembered in main. And if you want things to be remembered in main, you need to pass by reference. Okay, so now I comment to the user, create list to store the state of the game board. So that's what boxes is. So that's what Evan called it. So I kept that name the same. And now I have a function that just says, hey, initialize, right? So set up the game board for me, please. And so if I scroll down here to that function, it's void. Okay, it doesn't return anything. I pass the vector by reference because this boxes right here, this boxes vector, I want to set it up inside the function. If I'm going to set it up inside the function, then just like this function here, right? Whatever I do inside the function, I want to be remembered inside of main. Okay, if I'm going to initialize this vector in this function, it doesn't do me any good to then forget that I initialized it back in main. So I pass this vector by reference, and now I'm just setting each entry equal to 0, because that's how Evan denoted an empty box. So I pass boxes down here onto myVec. myVec now plays the role of the boxes vector, and then you're just setting each entry of that vector equal to 0. And since you passed by reference, those changes are remembered up here in main. So the game board really has been initialized. As you now move past this line of code, boxes now consist of n zeros, whereas just a second ago it consisted of nothing, right? It had n entries but nothing in them. Okay, so now let's move on. I tell the user the current game board is, and I print the game board, right? These functions are all suggestively named, right? So now let's go down to print game board. So printing the game board does what Evan made it do. It just went entry by entry through the vector, and if you see a 0, that means it's empty, so you print an E. If you see a 1, that means it's filled, so you print an O. Notice that this function doesn't return anything either, because I don't care about it returning something, I just want to print. So I just print and then I'm done. Notice also I pass the vector by reference. Okay, you have to be careful when you're doing this. The only reason I did that was because I wanted to save memory. So remember, we've talked about this before, that passing by reference saves memory because you're not making a copy of the vector when you're passing the vector itself. So I didn't mess with the vector at all. Okay, I didn't change anything. All I did was print what I saw. So I didn't make any changes, so passing by reference doesn't cause any changes up in main. But if in this function I were to now say, oh, myVec 0 equals 1 or something, you know, if I start making changes like that, they will be remembered. Okay, but I didn't make any changes. So let me go back up to main. So I've made sure they give me a number of the number that's valid. I've initialized the game board. I've shown the user what the game board is. Now I want to play the game. Well, you want to keep playing, right, as long as nobody has lost, right? So as long as nobody has lost yet is true, right? It's a true statement that nobody has lost. You want to play this game. So as long as nobody has lost yet, and how do you know if nobody has lost? Well, you need to know what the current game board is, right? So I feed the current game board into this function so the function can tell whether or not somebody has lost. So let's now go down to bool nobody has lost yet. Okay, what does that look like? Well, I pass the game board to this function, and what does this function do? It does what Evan made his check do in main before. This function just goes entry by entry through the vector, and if it ever sees 2 1s in a row, right, that's what this is doing. If this is a 1 and this is a 1, then they sum to 2. If you ever see 2 1s in a row, which means there are adjacent rocks, then you return false, right? Because now somebody has lost. If you see this, somebody has lost, so you return false. But if you make it all the way through the vector and you don't see adjacent rocks, then it is true that nobody has lost, and you should keep playing the game. So again, this for loop is just marching entry by entry through the vector, the current game board, and checking whether or not somebody has placed a stone adjacent to another one. If such a thing has occurred, then you return false because somebody has lost. But you return true if you don't find such a thing because nobody has lost, so this statement is true. Okay, so as long as nobody has lost, we keep playing. So where do you want to put your rock, right? And now I get the place from the user. And remember, in Evan's code, he had a check right after that. So basically, you want to make sure that this this choice right here isn't too small, it's not negative, isn't too big, it doesn't go off the game board, and you want to make sure this place, you want to make sure the user chose an empty box. Okay, so if this place represents a position that's already filled, that's not allowed, so the user must choose again. So all I've done is I've streamlined his check, and I say, hey, as long as they chose something invalid, right, so is valid is false, so as long as they've done something bad, let's make them update, So as long as they've chosen something invalid, so as long as validity is false, then make them update their choice. So let's now go to is place valid. So this is just what Evan had. Well, the place is A. That's what I've used to denote the place. And if you want to check if a given choice is valid, you of course have to hand the function the game board. How is the function going to know if your choice is valid if you don't hand it the game board, right? So this is a Boolean function where I tell it the choice the user has made, A, and I tell it what the current game board is. And so what this does now is it just checks, is this position choice too big? Is it off the right-hand side of the game board? Is this position choice too small? Is it to the left of the game board? Or did the user choose something that was already filled in? Did they choose a box that already had a rock in it? If any of those conditions is true, I return false. Okay, it's because it's invalid. Their input was invalid. But if I make it past all this, then that means it must have been a valid choice, and I return true. So up here, that's all this is saying. As long as they're choosing something invalid, we should make them update. Well, what does the update function look like? Here it is. Now I have to tell it the place, and for technical reasons here, I tell it the size of the board. So because if I'm going to make them update their choice, you have to know how big the board is. So if the board has size 5, then when you update this place, right, then the user can choose 0 through 4. But if the board has size 30, they can choose 0 through 29. Okay, so if you're going to make them choose a new position, then you have to know how big the board is to check whether or not that position is true or is valid, whatever. Okay, so please enter an actual empty position, and remember counting starts at 0 and goes up to the size -1. Right, so you're reminding the user of that. Then you get a new choice from them. And notice, since I passed by reference, this update will be remembered back in main. So let's say that back up here, where is this? Okay, let's say the user chose position 4. Okay, so that's what this is right now. Well, suppose that 4 is filled in. There's already a rock right there. What's going to happen is this is going to return a false value, and now you're going to update place, and you're going to feed in 4 right here, and you're going to feed in the size of the game board. And so then when you go down to this update place function, yeah, so this is now 4, right? But now you make the user try again, and now if they enter 5, and 5 is okay, then back up here in main, since you've passed by reference, back in main, this place right here has now been updated. You remember that change you made down in the update place function. Okay, so again, we're going to play as long as nobody's lost. Here's a validity check for a given choice that the player has made. Once we know their choice is valid, we update the game board, right? And I'll spare you the details of that in the interest of time, but it does what you think it does, right? You have to hand that function the game board, and you have to tell it the place where the user has made their choice, right? And then you just change a 0 to a 1, and you remember that you did that. And then once you've done the updating, you want to tell the user what the game board is now, so you just print it. And there you go, right? This loop will run as long as nobody has lost. Once somebody loses, you break out of this loop, you say you lost, right? And you're done. Okay, so I want to make a couple of closing comments about this example. The first comment is, neither my program nor Evan's original program are, quote, right. Neither program is more correct than another. The difference between the two is stylistic. So why would you choose to write a program the way I did? Why would you choose to outsource all of these tasks to functions? I mean, Evan's original game wasn't that long, right? It's not like there was a ton of code there, right? So why would you choose to write it the way I did? Well, hopefully that's clear, because suppose that you're a professional programmer. Here's the thing about professional programming. It's extremely collaborative, and once your code is written, what if you change companies, right? Now some other programmer is going to come in and try to see what you did. And you should try to make your code as readable as possible, right? So if you've written the code the way I have, right, a new programmer can come in and say, oh, they can look at main and get a really clear idea of the global structure of the program, right? Because I've named all these functions suggestively. So a new programmer can come in and they can immediately see the sort of core logic of my program without getting into the nuts and bolts of the program. Okay, this program, all the nuts and bolts are down here. Right? This is where all the real code happens and all of these functions. But suppose you don't care about the nuts and bolts. You just want to get an idea of the big picture. Okay, you want something holistic, a holistic view here. The way I've written this program lets you do that. A new programmer can come along and see exactly the logic I used. Oh, he made sure the number of boxes was valid. That's a good thing to do. Oh, he set up the game board. Okay. Oh, then he printed the game board. I understand. Oh, as long as nobody has lost, he's going to keep playing. Oh, here's a validity check. Okay, the user chose a spot. I guess you want to make sure that spot is valid. Oh, and then once you are valid, you update the current game board. That makes sense. Okay, and then you show the user the updated game board. Boom, right? A new programmer can come along and see that that's exactly what I did. Now, if the new programmer wants to make changes or whatever, right, then they have to get their hands dirty and come down here to these functions and mess with them, right? But the way that I've written this function means that somebody with even very little programming experience can come along and at least see the big picture of what I've done, right? So that's one reason why you would use functions. It really streamlines main, and if you name your functions appropriately, it really communicates to another programmer what you've done, right? So notice I have very little commenting in my program. Ordinarily I would use more comments, but I don't need to write a lot of comments here because I've named my functions suggestively. So the function names themselves are kind of like a comment to another user. Okay, so both Evan's original code and this modified code I have here, both of these will be on Moodle if you want to directly compare them side by side. Okay, so let's now move on to recursion. So to introduce recursion, I want to have you consider the following paradox. Okay, so we're going to start with a little bit of philosophy, I suppose. Here are three premises. The first premise is that living things are machines. Okay, so when you think about that premise, you might first think, oh, well, I'm a human, I'm not a machine, right? But machine here just means that, like, your processes are mechanical. And in particular, reproduction is mechanical. Okay, so reproduction is entirely understood, right? It's just this mechanical process, right? Sperm goes into egg, you reproduce. Or in the case of self-reproducing organisms, right, an amoeba just splits in two. It's a mechanical process. So with respect to reproduction, living things are mechanical, right? It's just a machine sort of setup. So that's premise one. And this is how biologists approach living things, essentially, right? Machine is just a catch-all term for something that, whose component parts you understand how they fit together, and you can make predictions, So anyway, that's premise one. Premise two is that living things can reproduce. Premise two is hopefully not controversial. Hopefully you agree with this immediately, okay? Premise three is that machines cannot self-reproduce. So you can't build a machine that can reproduce itself. So in other words, machines cannot asexually reproduce, if you like, okay? So here are three premises. 1 and 2 now, once I've explained what I mean by 1, hopefully 1 and 2 are just clear to you. Okay, you understand what they're saying and you understand that they are true. Okay, I'm going to give you an argument for 3 here in a second, but let me first point out that these 3 premises combined give you a paradox. What we've said here is that living things can both self-reproduce and also can't self-reproduce. Okay, so living things can self-reproduce, but living things are machines, and machines can't self-reproduce. Okay, so it's sort of a paradox or a contradiction, if you like. Living things can both reproduce and not self-reproduce, right? So how do you resolve this? Well, the first thing I want to do is argue for number 3. Maybe number 3 is the least obvious of these premises. Okay, so let's think about this. Consider a machine that constructs other machines, like a factory that's fully automated that makes cars. Okay? Well, the factory that makes cars needs to be more complex than the cars it's making, right? Because this factory has the car's design embedded inside of it. Okay, so if you agree with that, let me now just make this more general. If A is a machine that makes machine B, then A must be more complex than B because A has B inside of it in some sense, right? The design for B is inside of A already. Therefore, A is more complex than B. Well, what does that mean? That means that A can't produce itself because A can't be more complex than A, right? So if you agree with all this, right, what I'm really saying is, suppose that A could reproduce itself. Oh, but things that reproduce themselves, machines that reproduce themselves, are more complicated than themselves. Okay? And that can't happen. So hopefully now you agree that all 3 of these premises are true, and that's what gives a paradox. Okay? So it turns out that item 3 is false. Machines actually can self-reproduce. So it's sort of a fun exercise, a fun philosophical exercise to think through what's wrong with this explanation or this argument I've given right here. Okay, because if premise 3 here is false, that means there must be something wrong with my argument that claimed to prove item 3. Okay, so you can think through that on your own, but essentially that is false. Machines can self-reproduce. And the idea of self-reproduction is called recursion. Okay, so recursion is kind of a fancy name for machines reproducing themselves. Machines like, they're sort of a snake that eats its own tail or something. They sort of feed off themselves. They can reproduce, self-reproduce. Okay, so that's all sort of like high-level, I don't know, abstraction. Let me give you a real example of recursion. The way that we will use recursion is with functions. So that's what you are expected to do, to write recursive functions. And the example I'm going to show you is a function that deals with Fibonacci numbers. So if you don't know what those numbers are, here they are. You start with 0. The next number is 1. The next number is the sum of 0 and 1, which is 1. The next number is the sum of 1 and 1, which is 2. The next number is the sum of 2 and 1, which is 3, etc. Okay? So wherever you are in this list, the entry that you are staring at must be the sum of the previous 2 entries. Okay, that's how the sequence of Fibonacci numbers is defined. Okay, so the nth Fibonacci number is the number before it plus the number twice before it. Okay, so that's what the function is. Or sorry, that's what the sequence is. So let's write a function that takes parameter n and returns the nth Fibonacci number. So you want to input 4 and have it return the 4th Fibonacci number, which is 2. If you input 8, then it should return the 8th Fibonacci number, which in this case is 13, right, and so on. Okay, so let's write a function that does this. Whoop. Okay, so at the very least, if you're going to write a function that does that, Fibonacci numbers are, let me declare it like this. Fibonacci numbers are integers. So what you're going to get back, what the function is going to output, is an integer. And you want to feed in which of those you want, right? So this n value is just, hey, I want the 5th number, or the 8th number, or the 30th number, right? And the function is going to give you back the 5th number, or the 8th. or whatever you want. Okay, so now let's actually build the function. Well, first of all, if n equals 1, what do you want the function to return? You want it to return the first Fibonacci number. What's the first Fibonacci number? Oh, 0. Okay, so I'm going to make this I'm just sort of manually telling it, right? Hey, man, if you want the first Fibonacci number, return 0, right? If you input the second number, now you want the second Fibonacci number, well, that's 1. Right? So the first two numbers are just defined. The first number is 0, the next number is 1, right? Okay, what if you want some other Fibonacci number, though? What if you want the third number, the 8th number, whatever? Well, in that case, you need to do something different, okay? And what I'm about to do is going to blow your mind, okay? So fasten your mental seatbelt and hold on for this ride, okay? We're going to recursively define something now. We're going to have this function sort of self-reproduce, okay? And so before I write down what I'm going to write down, let me just point out that we've had examples where you can have this function here call on this function if it wants to. So you can have different functions call on other functions if you want. You know, main itself up here, right? It's a function and it calls on other functions. It calls on all of these functions down below. So functions can call on different functions. But actually, functions can call on themselves as well. So this function right here can call on itself. Okay, and that's called recursion. That's how sort of a machine self-reproduces. So what does that look like? Well, suppose that you want the nth Fibonacci number. Well, what is the nth Fibonacci number? It's the n minus first Fibonacci number plus the n minus second Fibonacci number. So what are we going to have this else return? Well, we're going to have it return nth fib number n minus 1 plus, oops, I guess I have to capitalize it, plus nth fib number n minus 2. Okay, boom, right? Check that out. So this function is like reproducing itself. You're calling on it inside of itself, right? So it's like a snake eating its own tail or something, right? So let's talk through the logic of what's going to happen here. Suppose I feed in the number 1. Well, it returns 0, because that's the first Fibonacci number. Suppose I feed in the number 2. Well, it's going to return 1, because that's the second Fibonacci number. What if I feed in the number 3? Okay, well, if I feed in the number 3, I skip past these two things, right? And now I'm down here in the else. Now it's going to return nth fib number 3 minus 1, which is now 2, plus nth fib number 3 minus 2, which is 1. Okay, so it's going to return this with a 2 inside, plus this with a 1 inside. But this function knows what those are, right? If this value here is a 1, the function knows to return a 0. If this value here is a 2, the function knows to return 1. So if you feed in a 3, it just reaches back and returns the 0 plus returning a 1. Suppose you feed in a 4. Okay, well 4 is not 1 and it's not 2, so you skip over these. Now you do nth fib number 3 plus nth fib number 2, right? Well, nth fib number 2, the function knows what that is because you've hard-coded it. Nth fib number 2 is 1. Well, what about nth fib number 3? The function doesn't immediately know what that is, so it recursively finds it like we just described, right? Nth fib number 3 is now nth fib number 1 plus nth fib number 2. Okay, so imagine you feed in the number like 8 right here. Well, 8 is not 1, 8 is not 2, so you skip over this, right? Now it returns nth fib number 7 plus nth fib number 6, but it doesn't immediately know what those are. Nth fib number 7 is nth fib number 6 plus nth fib number 5. It doesn't know what those are, right? It just keeps going though. So you set off like a chain reaction where this function calls on itself a bunch of times, right? But since you hard-coded a starting point, okay, so this recursion has a seed or a start point where you know that if you have a 1, you give a 0 back, a 2, you give a 1 back. you set up a chain reaction that's just like chain, 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 and then all the way back down to these values. And then the function can then build itself back up to where you want. Okay, so after saying all that, let's come here and let me clear out all of this, and let's have it print nth fib number. Let's just have it print out the 6th number in the sequence, right? So what should that print? Should print 5, I suppose, right? That's the 6th number in the sequence. And it does. Okay, that's good. Try it again and put the 10th number. Prints out 34, okay? Was that my list? Not quite. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So the next number in the sequence is the sum of those two guys, which is indeed 34. Okay? And you can, of course, use this function like, what if you want to print out the first 30 Fibonacci numbers, or the first 40 of them, whatever. Well, you can do that by just setting up a for loop that prints out the first 40 of them. So let's see out nth fib number and just go through them one by one, right? So we'll print out the first one, print out the second one, print out the third one, etc. And I suppose we should separate them somehow so it looks nice. So let's see what that does. Yeah, so it gets kind of big, kind of fast, right? But here we are back at the beginning, 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, etc. So it does it for us, right? Yeah, these sums start to get big, right? So once you start adding 6-digit numbers, you quickly build up into the hundreds of millions here, or whatever this is. Okay, so that is the idea of recursion, or at the very least, the idea of a recursive function. It's a function that calls on itself, right? This sequence here is recursively defined. The value of this guy right here depends on previous values in the sequence. All right, that's what it means to be recursively defined in mathematics anyway. So the nth number depends on what the previous two numbers were, right? And if you want to start computing sequences like that, you use a recursively defined function that just eats itself, right? Sort of feeds on itself. Okay, so that's the last topic for functions. So we are now done with functions. So in class, I'll give you some other sort of recursive things to play with. This is a cute idea. So we'll deal with recursion and a little bit more of passing by reference in class. Okay.